Decades, the world of cloud computing has had one undisputed champion, the x86 architecture. It's been the king. But now, there's a new contender stepping into the ring, an ARM-based processor called Graviton. So in this explainer, we're going to break down this epic showdown to see if the reigning champ can really hold its ground.
But listen, this isn't just about geeky tech specs. This is about your bottom line. It all comes down to a really simple but huge question. Is it possible you're overpaying for your cloud performance and you don't even know it?
To really get what's going on here, we have to pull back the curtain a bit, because at their core, these two processors aren't just different chunks of silicon. No, they represent two completely different philosophies about the best way to get work done.
Okay, let's use an analogy. Think of x86 with its CISC architecture. That stands for Complex Instruction Set. It's like a fancy Swiss Army knife, you know? It's packed with tools and can do really complex multi-step tasks with a single command. On the other side, you've got Graviton, which uses RISC, the reduced instruction set. This is more like a perfectly honed set of specialist tools. Each tool does one simple thing, but it does that one thing incredibly well and super fast.
And that fundamental difference in philosophy, well, it leads us to maybe the most critical metric in the cloud today, performance per watt. See, it's not just about raw speed anymore. It's about how much processing power you can squeeze out of every single unit of energy you pay for. And it's right here, on this battlefield of efficiency, that Graviton is making its biggest claim.
So enough with the theory, right? How do these very different approaches actually perform in the real world? Let's put them to the test. We've set up a high-stakes gauntlet to find out.
We're going to run a tough, 3-round gauntlet that covers some of the most common cloud workloads out there. We'll kick things off with modern containerized apps. Then we'll move on to the workhorse of the entire internet, databases. And we'll wrap it all up with the really heavy lifting of machine learning.
So, in round one, with containers, a really clear pattern emerged almost immediately. The Graviton instances scaled way better. This is that RISC architecture in action, because its instructions are so simple they can be processed in parallel with incredible efficiency. It ended up managing more containers per CPU, which means you get way more throughput while using fewer resources. A clear win.
Now for round two, databases. Things get a little more nuanced. It's not a simple knockout. For workloads that are really read-heavy, think about serving up a popular website to millions of users. Graviton's efficiency gives it a major lead in transactions per second. But for tasks that are write-intensive with lots of complex updates, that powerful Swiss Army knife approach of x86 still holds a bit of an edge.
And in our final round, the heavyweight division, machine learning. Graviton really proved it's a serious competitor here. It delivered some really competitive training times, especially for tasks that can be broken up and processed in parallel across all its cores. What this all means is that it offers an absolutely fantastic cost-to-performance ratio for training your ML models.
Okay, the tests are done, the dust is settled, we've seen how they perform, but that's only half the story. What does all of this mean when the bill actually arrives? Let's dig into the data and declare a verdict based on that crucial intersection of raw power and cold hard cash.
So take a look at this first chart. This is pure throughput, basically how much work is getting done. Under the exact same load, the data is crystal clear. Graviton is processing a significantly higher volume of transactions than x86. That's a straight-up win on raw output. More customer requests handled, more work finished.
But here's the kicker. How did it achieve that? This next chart tells the whole story. It reveals that Graviton used a lot less CPU power to do it. So it's not just working harder, it's working smarter. This right here is that performance per watt efficiency we were talking about, visualized.
And when you combine those two things, getting more work done while using less effort, you get this. A truly staggering number. A potential for up to 40% cost savings per transaction. This is the kind of real-world business impact that changes the game.
This final chart brings it all home. It shows the bottom line, the actual cost per transaction. And it just visually confirms everything we've seen. Graviton's incredible efficiency translates directly into a lower dollar cost for every single request your application serves. When it comes to the all-important metric of value, the challenger has a decisive edge.
So, we've seen the data, we've seen the results. The big question now is, how do you apply this to your own work? It's time to move from this competition to your strategy. Let's build your cloud playbook.
Okay, here's your cheat sheet, your game plan.
You're going to want to choose Graviton when you're running those modern, containerized applications, when you're dealing with read-heavy databases, or frankly, whenever your number one goal is just pure cost optimization. But you want to stick with x86 for now if you have those really write-intensive database needs, if you're stuck with specific legacy software, or if you need absolute, single-core, peak performance above all else.
The key takeaway here is simple, but it's profound. For years and years, the choice of what processor to use was an afterthought. It was a default. Well, not anymore. It's now a core strategic decision that directly impacts your performance, your cost, and your overall efficiency.
The Challenger is absolutely proven it can not only compete, but that it can win in some really key areas. And that has fundamentally changed the entire landscape. So the question we're all left with now is, what does this intense new competition mean for the future of cloud computing? And what kind of amazing